variation functions. So we're going to be looking at all the different types of variation functions, and involved in this there's direct variation and inverse variation, things that we've looked at before. And then we're also going to put in there something that's called joint variation and combined variation, which is going to throw a whole bunch of different variables in together. And this is, a lot of this is working with word problems, so you get to expand your knowledge of word problems, and hopefully you'll be successful with them. Right, Sam? So direct variation is a relationship to variables x and y, and can be written in the form y equals kx. So it's a linear relationship, and so as one thing changes, the other thing changes the same way. So if it's direct variation, as x gets bigger, y is going to get bigger, and as x gets smaller, y is going to get smaller. And it's like a linear relationship. Okay, so the only difference between a direct variation and linear is the fact that the y-intercept is always 0 for direct variation. And so we have this function for direct variation, y equals kx, where k is called the constant of variation. That's the thing that doesn't change. But what's another name we could give k? What's something else we could call k? What do we call that thing in front of the x when we're talking about a linear relationship? Starts with the letter S. The slope. Okay? All right? It's the slope. So all this is what's happening to x all the time, and that, or whatever happens to x, that's happening to y as it gets bigger or smaller. So we're going to look at writing and graphing direct variation. Okay? Now, the other thing is we need to understand is that if y equals k times x, it's important because you need to be able to find the constant of variation. And quite often, that's the thing that's not given to us, and we need to find it. So if I want to find k, what will I do? Y over x, yep. Okay. So the constant of variation is equal to y over x. All right, and so we'll get you a note card in just a moment too. So here they have y varies directly as x, and this is the thing you're looking for. All right, when we're talking about variation things, there's a specific thing. It's going to say this varies as this thing does. Either it's going to say directly or inversely or jointly. And all those things are the key words for you. If it says y varies directly with x, that means that we are going to have y equals kx. That's the direct variation. In here it says as when y equals 27, when x equals 6, it says write and graph the direct variation function. So we need to find the value of k to be able to write the function, the constant of variation. So I find k by doing y over x. So k in this case is equal to 27 over 6, which is what? Can I reduce that fraction? Say 3 goes into both of them, right? So it's 9/2. So my constant of variation is 9/2. So my direct variation function is going to be y equals 9/2 x. And how do you remember how to graph linear functions? What's the first thing I graph when I have a linear function? The y-intercept. Okay? So we graph the y-intercept first, and the y-intercept on a direct variation function is always going to be the origin. And then I graph what? The slope from there, right? So from that point, I'm going to do the slope, which the slope says 9/2, right? Is that 9 the x or the y? Okay, it's the y. It's change in y over change of x. So I go up 9 and over 2 from that spot, and I draw my line. So I have my function and my graph with arrows on it. Okay. So all direct variation is y equals kx. The y-intercept is always going to be 0. Okay. If it has a +2 or +3 or -7, then it's not direct variation. Okay. It's just a linear relationship. All right. Now, when we have direct variation problems, so if we have a word problem usually with direct variation, and they have more than one part to it. In other words, they might have 2 parts to this. And talking about 2 different situations. Well, we have, if there's 2 different situations, we can do x sub 1 and y sub 1 and x sub 2 and y sub 2 to relate the 2 different parts. And with relating the 2 different parts, we actually can develop a formula for a direct variation problem, which basically just says that those 2 ratios are going to be equal to each other. Okay. That if I have y sub 1 equals k times x sub 1, then k is y sub 1 over x sub 1. Y sub 2 equals k times x sub 2. Well, k is y sub 2 over x sub 2. And in this situation, these 2 k's are the same thing. So that means that I can say that these 2 ratios then are equal to each other. So what we end up doing is just ended up with a problem that solves a proportion. And so most direct variation problems can be solved just using proportions. And how many of you know how to cross multiply? Okay, so in that warm-up you did it, and we're probably successful with that, right? Since nobody had any questions on it. Okay. So here we've got the cost of an item in euros. Cynthia, you don't use euros in your country, do you? No. What money value do you use? Yeah. What do they call your money? Yen? What? Okay. How's the dollar compared to that? Okay. So the dollar is worth more. All right. Okay. That's unusual. The dollar's not worth a whole lot these days. Okay. Cost of an item in euros varies directly. So here's my key right here again. Varies directly as the cost of the item in dollars. Says when E equals 3.85 euros, when D equals $5, find D when E equals 10 euros. Okay. And this is actually just a simple problem that you can write it as a proportion. All right, and we're going to go ahead and look at that first. So we can say that euros 1 is to dollars 1, as euros 2 is to dollars 2. Because this is a direct variation problem, I can just set it up as a proportion and solve it. So 3.85 is to 5, as 10 is to D. And I'll just call it D there. I don't need to put D sub 2. And what's your wording then? Cross multiply and divide, right? Right, that's a shortcut way that Mr. Bromley taught you back in the day, or whoever it was. So we get 50 divided by 3.85, which is what? Now let me ask you this, okay? Is D going to be bigger than 10 or less than 10? Okay, it better be bigger, right? Because 3.85 is to 5 as 10 is to. And Chase got $12.99. You guys agree with that? Okay. Do I need to put a dollar sign with that? No, because this represents dollars, right? Okay. They didn't use dollar signs here, so I don't need to use it there. Now, you could have done it the second way. You could have found the value of K first of all. I could have set it up that since it says E varies directly as the cost of the item in D dollars, then that means that E is equal to KD. When it says this thing varies directly as the other thing, that means that the first thing is your Y, the second thing is your X. So we could have used these first two numbers to find the value of K. All right, that constant of variation. And so what's 3.85 divided by 5? Point what?
0.77.
0.77, okay. All right. So we could have found that the constant of variation in this case was 0.77 and then use that with it. So then it said the euros was 10, constant variation 0.77 times D. Right. Where scenario 1 gives me K, scenario 2 then I can use that to find the value of D, which better be 12.99, right? Okay. So you have two options for solving direct variation problems. I like the proportion much better just because it's quick and easy, right, for setting up. But the key is we're looking for varies directly. And here they give me three numbers, plug them into proportion, I'm able to solve it. Okay. Now the next thing we'll look at is what's called joint variation. Right? So we have all these variations, but so it's very important, okay, that you keep them straight. Right? Direct variation, linear relationship between two variables. Joint variation, though, adds another variable to it. In joint variation, that's y equals kx. We still have that, but then we're adding another variable to it. Okay? So there's actually three variables we're talking about. In this case, it'll say that y varies jointly with x and z. Okay? So the key I'm looking for there then is when I have a question is, it says varies jointly. Okay? So whenever it says varies jointly, it's going to be a relationship between y, your constant of variation, because k is still involved with this, and then two other variables. So this problem says the volume of a cone varies jointly as the area of the base and the height. So when I start out to write my initial problem then, I've got, not y. Okay. It says V varies jointly with the capital B and lowercase h. The volume of a cone, y'all know what a cone looks like, right? Okay. And this is not your regular ice cream cone. This is a more like, what kind of a cone? Okay, a waffle cone, or what's the other thing they call those other smaller ones?
Sugar cone.
a sugar cone, okay? All right, so that would be that type of a cone. So when I set it down, upside down, then I get that point to the top. All right? So it has the area of the base, which is, hey, what is that shape? It's a circle, okay? And how do I find the area of a circle? Pi r squared, okay? All right. So it says the volume of a cone varies jointly as the area of the base and the height. So this is a really interesting question because, all right, I'm multiplying the area of the base and the height. So we're actually developing the volume for a cone. How to find the volume for a cone. Okay. All right. Area of the base times the height. We just need to find this value of k, this constant variation. So it says, and v equals 12 pi when b equals 9 pi and h equals 4. So here we've got a situation. They give us all of those key values, v, capital B, and h. And so what's missing from there? K is. So we're going to find that constant of variation. So we plug those numbers in. We have 12 equals, 9, oops, it's 12 pi, excuse me, equals k times 9 pi times 4. Notice, okay, a couple things. The units are important here. The volume is in cubic feet, right? Ft cubed. The area of the base is in square feet, and the height is in feet. Now, when I find the constant of variation, will that have a unit attached to it? Yeah. Does the constant of variation have a unit attached to it? Because 9 pi is square feet, right? 4 is in feet. So if I multiply square feet times feet, what do I get? Okay, cubic feet, right? Which is what my units are for the volume. So the constant of variation does not have a unit attached to it. Right? So make sure when you find that you don't put a unit with it. So we're going to divide here by 36 pi, right? 9 times 4 is 36. Now, there's no reason to use that pi key on your calculator. It's just like if we had a x here. All right, if this had 12x over 36x, the x's would just cancel, right? So the same thing is the pi's cancel, and so I get k is equal to what? 1/3. Okay. So the volume of a cone is equal to 1/3 pi r squared h. Now, you don't have to write that down. I'm just telling you, we just developed that formula. Right? Because you told me that the area of a circle is pi r squared, correct? And the base of the cone is a circle. So there's the volume of a circle right there, or of a cone. We just figured it out. You guys are pretty smart. Right, Chase? So it says find B. All right, so we're going to find B when the volume is 24 pi cubic feet and the height is 9. So we've got, 24 pi equals 1/3 times the base times the height, which is now 9 feet. All right, Spencer, what's 1/3 of 9? 3. Okay. So we get 24 pi is equal to 3b, because I just multiplied that 1/3 times 9. And when we divide by 3, we get what? Okay. 8 pi, and what's my units for that 8 pi? Okay. Square feet, because we're talking about area. Remember, area is two-dimensional. So here's the big question for you. Let me rewrite this. What's the radius of that cone? What's the radius? So we would get a radius here, which you didn't ask me that question, but it's good to know, right? A radius of square root of 8. Good question. All right, let's see how you do here then. Okay. No, we have 2 more. That's number 3. What's that? No, all joint variations will not be cones. Okay. All right. Oops. That's where I came from. All right. Third type of variation is called inverse variation. That other page came because I did 8.2 before 8.1 in the past sometimes. Okay, inverse variation means that x and y do the opposite. When x gets bigger, y gets smaller. When y gets bigger, or if x gets smaller, then y gets bigger. And so this is y equals k over x. Because what happens if I divide by a bigger number? My result's going to be smaller, right? And when I divide by a smaller number, my result's going to be bigger. Okay? So inverse variation is as the one gets smaller, the other gets bigger, or vice versa. And in this case, then, k is equal to what? Okay. X times y. So make sure you pay attention to the difference between direct and inverse. Direct, y equals kx. Inverse, y equals k over x. And so knowing the difference between them makes things easier.
Does k always equal xy?
If it's inverse variation, k is always equal to xy. Yep. So this says y varies inversely. Like I said, we're always looking for that. Okay? Varies jointly, varies directly, varies inversely. I'm looking for any of those 3 things. Okay? Direct, joint, inverse. So we got y equals k over x. Says when y equals 4, or y equals 4 when x equals 5. So that means that k is equal to what? 4 times 5, which is 20. So my function is y equals 20 over x. There's my function. And here's a little helpful hint. So if you don't have a calculator, even if you do have your calculator, for graphing an inverse variation, it says use values of x that are factors of k so that the y values will be integers. Right? Because there's no y-intercept here, right? What's 20 divided by 0? That's one word for it. It's undefined, okay? All right, you can't divide by 0. So we're actually going to have asymptotes in this case, because this graph then looks like this. Because is the graph ever going to touch the x-axis? Is it going to touch the y-axis? No, okay, so make sure your graphs don't do that. But we have, so if I graph this then, I want to choose values that are going to give me integers. So if I put, let's think about this, okay? Let's see, what's a number that goes into 20 evenly? 2 does, okay? All right, so if I do 20 divided by 2, what am I going to get? 10, all right? So I have the point 2, 10. All right? And what's another number? So I also have, if I have 2, 10, I also have 10, 2. 10 to what? It's not 10, 2 yet, it's 22. Come on. I know, I'm not very funny actually. Okay, what's another? 4 and 5. Okay, so I have 4, 5, and 5, 4. Okay, and I can use those numbers to make my graph. But I also have these down here in the third quadrant, right? Well, down there I have the same numbers except they are going to be negative. Okay, negative 10, negative 2, negative 5, negative 4, negative 4, negative 5, negative 2, negative 10. Right? So make sure that if it's inverse variation, when you draw this graph, that you show that it does not cross the x and y axis for one, but that you have both quadrants. Now, what if k is negative? The asymptotes are going to be right where they are. Okay? The asymptotes are going to be where they are. The asymptotes are the x and y axis. Okay? The graph is, right, okay? If I get a negative 20 here, or k is a negative value, then my graph's going to be in the, which quadrant is this one up here? Second and the fourth, okay? All right. Second and the fourth. All right. Go to that one. Do we need to do a practice one on them?
No.
All right, because you want me to hurry up and get done, right? Okay. All right, so I'll just write this one down so if anybody wants to look at it later. So in this case, y is equal to 40 over x, and that graph then would look like this. All right, so I would make my window bigger then. So you can see it. Okay. All right. Okay. So let's look at an inverse variation problem. All right, we did direct variation problems, inverse variation problems. Well, with direct variation problems, we had this, oops, come back here, real nice relationship here that said this proportion, y1 over x1 equals y sub 2 over x sub 2. But when we found out the inverse variation, we said, hey, k is equal to x times y. So that means that we're not doing a proportion here, but we're doing what they call, I forget what they call it, a product. Okay, all right, but it's not really a proportion. But in this case, then, we're going to have the product of x times y is equal to the product of x times y. They both represent the same value of k. So if you have an inverse variation problem, then you're going to have two products that you're going to, two products that you're going to set equal to each other. Okay? Where with direct variation, we did two ratios that we set equal to each other, but they all just represent the x and y. Okay? All right, here we go. Sports application. All right, we all love this. Running. Hey, there we go for you cross-country stars. The time needed to complete a certain race varies inversely. There's what I'm looking for. How does it vary? It varies inversely as the runner's average speed s. So that means that T equals K over S. Or if I want to set it up, I can set it up like this, that T sub 1, S sub 1 is equal to T sub 2, S sub 2. All depends on which method you want to do. If a runner with an average speed of 8.82 miles per hour completes the race in 2.97 hours, what's the average speed of a runner who completes the race in 3.5 hours? So, really nice. 8.82 times 2.97 equals 3.5 S. So we set it up with the variables we know, T and S, and plug in what we know and find the missing part. What's S, Abby? 7.18? 48, okay. All right, do we have any units for that? Miles per hour? Okay. Miles per hour. All right. Okay. Or we could set it up like this, say K equals 8.82 times 2.97. Right. Then when T is 3.5, what's K? What's 8.82 times 2.97? 26.19 divided by S. That's a little bit tougher to solve then, isn't it? Okay. But if you remember, we talked yesterday or the other day about doing the reciprocal, right? In those situations. So I could just flip this over, but I'd have to flip this one over too, so it'd be 1 over 3.5, okay, to be able to find the answer. Okay. Now, here's my question for you. What does K really represent? Okay, and what kind of a race was it? All right, Cynthia knows, but I want the rest of you to figure it out. What kind of race, or what does K really represent?